The most powerful naturally aspirated V8 engine in a production car ever. Hello everyone and welcome. In this video we're going to take a deep dive into the 2023 Corvette Z06 engine. GM provided me with access to several of their engineers who developed this engine to discuss in great detail the inner workings. The 5.5-liter naturally aspirated V8 engine is making 670 horsepower, which is especially crazy when you realize that's more than the larger supercharged engine that it replaced. So how in the world is that possible? Well, we're going to cover all the details, but I want to just take a moment to appreciate how cool this engine is. So ultimately, how much power you make with an engine is restricted by how much air you can shove into that engine. So you shove a ton of air in the engine, you put an appropriate amount of fuel with that air, you ignite it, boom, and you make power. And so what's really wild about this engine is that, so the previous generation Z06 had a 6.2-liter V8 engine. This is a 5.5-liter V8 engine, so both V8s, but it is now smaller. The previous engine had a supercharger putting in an additional 9.4 psi of boost, so additional air shoved into that larger engine. And yet, if you look at the horsepower figures, 670 for the smaller naturally aspirated engine. It's reliant on the atmospheric pressure around it, and it is making more power, 20 more horsepower, with a smaller engine at atmospheric pressure. How? So a big part of the story of this engine is how high it revs, an 8,600 RPM redline, making peak power at 8,400 RPM. So I made a way oversimplified quick comparison between these two engines to help illustrate that point of how much air you can shove into an engine ultimately is going to help you determine how much power you can make. And so if we look at our new Corvette Z06 engine, well, we are reliant on atmospheric pressure, 1 atmosphere going within that engine cylinder. We have 5.5 liters to work with, so we multiply that together, and we are revving to 8,400 RPM. So if we look at how much air goes into that engine per minute, well, we take 8,400 RPM, we divide it by 2 because we have 1 intake stroke for every 2 rotations of that crankshaft. We multiply all this across, and we get a number of about 23,100 liters per minute. Now, if we look at the C7 Z06 engine, well, we've got 1.64 as our pressure within those cylinders because we're adding in 9.4 psi of boost. We multiply that by the size of the engine. Of course, that's an advantage. Both that is an advantage, the pressure within it as well as the displacement. However, we do lose out a bit because the RPM is not as high, so we're not sticking as much air per minute, from an RPM basis, as we're not revving as high. So we multiply all that across and we get a number of 32,500 liters per minute, which is still 1.4 times what we are doing with the C8 Z06. So it still does have more air per minute, and thus you would think, okay, well, it's probably going to make more power, right? So what are the other factors that we're not considering? Well, first of all, temperature. So a supercharger is compressing air, and as you compress that air, it heats up. So hot air has less density than cool air, and a naturally aspirated engine is going to tend to bring in cooler air because you're not compressing it within that supercharger. So because it's naturally aspirated, the engine is going to be cooler. It's going to have a bit better density. So it's not realistic that we're actually going to get 1.64 cool temperature atmospheric pressure within it. The pressure will be that, but the temperature will be high. So your actual density of that air isn't as high, meaning the amount of oxygen you have to burn is actually less. Also, with our 5.5 liter V8 in the new Corvette, we have a compression ratio of 12.5 versus 10 in the previous engine, so that means we're squeezing that air and fuel more, which gives you better thermal efficiency, means you make more power. And also, this naturally aspirated engine, even though there's just atmospheric pressure outside, it's able to pull in just slightly more with some very clever tricks. It's able to pull in slightly more air. And so when you add that all up, realistically what you get is this smaller, higher revving V8 engine, naturally aspirated, making more power than the previous generation Z06. Now, a defining characteristic of a high revving engine is often a wide bore with a short stroke, and that is the case with this engine, 104.25 millimeters across that cylinder, and then that piston is moving down 80 millimeters. This is a really high bore to stroke ratio. I didn't do a ton of research, but I looked at quite a few cars out there, and I didn't see any that had a ratio this high as far as production cars. And that short stroke, of course, is helping you to rev really high. Next, let's talk about the engine's flat plane crankshaft. So traditionally, Corvette engines have a cross plane crankshaft, meaning the crank pins are split by 90 degrees. These crankshafts are heavy because they have large counterweights to counteract the forces of the pistons moving up and down. A flat plane crankshaft, on the other hand, has all of the crank pins on a single plane. You might call it a flat plane. The piston's primary forces are already balanced, so the crankshaft is lighter overall, which means it has less inertia and can rev very quickly. So if you look at the rotating assembly of the new Z06, you can see the forged steel crankshaft, which is significantly lighter than the previous crankshaft design, and you now have lightweight forged titanium connecting rods and the short height forged aluminum pistons. So the whole idea of using a flat plane crankshaft, and Corvette's philosophy here, is to remove as much reciprocating and rotational mass as possible. The other advantage of a flat plane crank is how it impacts your firing interval. As you can see, on a cross plane crankshaft, instead of the firing order always alternating from one cylinder bank to the other bank, sometimes the same cylinder bank will have two cylinders fire before switching to the other. Now, if you look at the new Z06, you can see that firing order switches between each cylinder bank. So it goes 1, 4, 3, 8, 7, 6, 5, 2, back to back each time. And so this is ideal for intake and exhaust tuning. And you can also see that you have this 4-2-1 exhaust. So the two inner cylinders and then the two outer cylinders. And if you look at this firing order, you can see it alternates between these two sides as it alternates between the left and right banks. And so what that does is it provides ideal exhaust scavenging by making all of those pulses evenly spaced. Now, the way I've drawn it here isn't actually accurate. If you look at the actual engine, you can see that those are all equal pipe lengths leading into that 4-2-1 exhaust. Moving on to the valve train, there is a lot going on. Instead of a single camshaft with 2 valves per cylinder, now we have dual overhead camshafts with 4 valves per cylinder. Truly the future. Looking at the camshafts, you can see they are hollow to help reduce rotational inertia. These cam lobes directly act on the mechanical finger followers, and there is no hydraulic component to this valve train. This gives you very direct motion for the valves. Moving on to the valves, you can see that they're using dual valve springs, so each valve has 2 springs. And so we have an engine here which has a really wide RPM range, right? And so if you're to hit the resonant frequency of one of those valve springs, well, with that spring resonance, you lose control of the valve. So they have 2 different size springs so that you can maintain good control of that valve moving up and down across the entire RPM range. So they have a larger spring for high RPM control and a smaller spring for low RPM control. Of course, they're both going to be used at all times. They're both always being compressed and released by that cam lobe. However, having both of those springs together ensures you don't lose control of the valve. The intake valves are titanium and the exhaust valves are sodium filled to help dissipate that heat. Now, you might be wondering, if there's no hydraulic component to the valve train, does that mean you have to manually adjust the valve lash over time? According to Chevy, nope. So there's a shim which you can see located between the tip of the finger and the valve stem. All of these engines are hand-built in Bowling Green, Kentucky, but GM has automated the shim selection during the head subassembly. A robot will pick the exact shim needed for each individual exhaust or intake valve, and it will have a process of checking the measurement 3 times throughout the assembly to ensure the perfect fit. The materials used and their surface finish keeps the part within tolerance for the vehicle's lifetime. So how do they know? Well, they run tests. They abuse the engine under severe conditions and ensure that the valve lash remains within spec under testing. There's also an oil jet in the finger that shoots through the opening in the finger follower to constantly supply fresh oil to the camshaft lobe. Another clever thing they've done with this engine is they've located the direct fuel injectors on the exhaust side rather than on the intake side. And there's 2 good reasons for doing this. First of all, it gives you more real estate for your intake valves. So this engine has massive intake valves, and that's really important for that high RPM air to enter into the cylinder. Second of all, this helps with emissions. So how? Well, with an engine of this style, wide bore, short stroke, when you're driving around, city traffic, low RPM kind of driving, you don't have really high piston speeds. So if that piston isn't moving up and down really fast, you don't have really good tumble and mixing within this cylinder. So by putting that direct injector across from the intake air, they collide together and it helps mix that air and fuel even though you have relatively low piston speeds, and so that helps out with emissions. Finally, we get to the intake manifold, and what a beautiful piece of engineering. engineering. So we have dual throttle bodies, dual plenums, 3 center valves, and then 4 trumpets which are mirrored on each side. So the benefit of this style of an intake manifold has to do with Helmholtz resonance. Big cool science word. So what is Helmholtz resonance? Well, when you're driving in your car and you roll down one of the rear windows, just one window, and you hear that really annoying wind buffeting, that's Helmholtz resonance. So you have these pressure waves bouncing around in here. Air acts like a spring, and that air is just bouncing all around with these pressure waves in here. And as you open these different valves in here in different combinations, you allow those pressure waves to travel around these plenums in different ways. And so you can optimize each of these for different RPM. So what do? Well, you don't have to understand perfectly how it works to understand why it's beneficial. All you do is you stick this engine on a dyno, and let's say you just leave all of them closed, and then you rev it from idle all the way to its 8,600 RPM red line, and you draw out that torque curve. So you got torque versus RPM, and that torque curve will have some peak. Then you open up one of the valves and you do the same thing again. Idle to red line, plot out that torque curve. What does it look like? Then you try a different valve. You try all the different possible combinations that you can enable by opening and closing these different valves, and you plot out all of those torque curves from idle up to red line. And then what you do is you just find these peaks and you choose, okay, at this RPM, we're going to use this combination of valves open. At this RPM, we use this combination. And then at this RPM, we use that combination of certain valves opened and closed. Now Corvette, they gave me a little bit of insight. At idle, all of these valves are closed. At 2,800 RPM, they're going to open up one valve. At 4,200 RPM, they open 2 valves. At 5,600 RPM, they close a valve. And then at 6,800 RPM, they close all the valves. And that gives them that ideal torque curve where you just follow these individual peaks based on that resonance that's going on within these chambers, those pressure waves, to maximize the torque of the engine. So how well did Corvette do? Well, let's talk about BMEP, brake mean effective pressure. I have a separate video if you want to learn all the details. I'd recommend checking that out. But basically, brake mean effective pressure is a nerdy way of comparing car engines. It tells you what the average pressure is pushing down on that piston. And it's good for comparing naturally aspirated engines. So if we look at a really impressive naturally aspirated engine built by Cosworth for use in the Aston Martin Valkyrie, this engine revs past 11,000 RPM, produces 1,000 horsepower. It's big V12, 6.5 liters. Well, if we look at its brake mean effective pressure, it's 14.3 bar at the engine's peak torque, and it's 13.1 bar at the engine's peak horsepower. So we'll just use these numbers for comparison. Now keep in mind, the Valkyrie is a $3 million vehicle. That's starting price, $3 million. So this Corvette Z06 is probably going to be about 3% of the cost of this Aston Martin Valkyrie with its wild Cosworth engine. The Corvette numbers for peak torque, brake mean effective pressure, identical, 14.3 bar and 13.1 bar at peak horsepower. So wild that in something, a 30th of the cost, you're getting that level of engineering put into it. Absolutely incredible engine that Corvette has produced here for this Z06. Thank you all so much for watching. If you have any questions or comments, of course, feel free to leave them below.